Hello students, in our earliest lectures we derived the matrix for the translation of a light ray through a homogeneous medium, and then we derived a refraction matrix for a spherical interface, and then we found that how to transform that spherical that matrix from a spherical interface to a plane interface. And then in our next video we derived the matrix for the reflection from a spherical mirror. Now in today's lecture we are going to derive the matrix for a thick lens and then for a thin lens. So here we have considered our thick lens, which is having some thickness t. Here the radius of the first interface is r1, while the radius of the back interface is r2. Here we have considered to the left side of the lens the refractive index is n1, to the right side of the lens the refractive index of the medium is n prime, and the refractive index of the lens is nl. So here when a ray of light from a point source is approaching towards the thick lens, which is having some angle alpha naught with the optical axis, and after refracting from the first interface, so there is no change in the height of the ray but only change in angle. This angle here this angle with the optical axis of the refracted ray is alpha 1, and again the ray again here refracts, but from this interface to this one there is a translation of ray and there is a change in height of the ray. Here the height of the ray was y1 and it was equal to y0, but here when it reaches this point the height of the ray becomes y2, and at the back interface when the light ray again refracts, so at this point the height of the ray doesn't change, while again only angle changes. So the angle of the emergent ray with the optical axis here is alpha 3. So our job in this topic is to find a matrix which is used to give us the final coordinates y3 and alpha 3 in terms of the initial coordinates, which is y0 and alpha 0. Therefore, from the given figure, referring to the figure where we have chosen the simplicity a lens with positive radii of curvature. For simplicity we have chosen the radii of the curvature is positive, and for the first refraction the corresponding matrix is for the first refraction here at this point. This is y1 because at this point the initial coordinate was alpha 0 y0, and after refracting from the first interface the coordinates are now y1 alpha 1. So y1 alpha 1 we are writing in matrix forms. This is m1 times y0 alpha 0. This is for the first refraction. Here m1 is the matrix representing the refraction through a spherical interface. And let me write it here. M1 is one L sorry, this is 0. This is 0 because here there is no translation. 1 0 n minus nl upon nl r1 into n upon nl. This is M1. Clear? Now similarly, for the translation of the light ray inside the lens is, here the initial coordinates are from here to here. The initial coordinates of the light ray are alpha 1 and y1, and when it reaches this point the coordinates become y2 and alpha 2, but during the translation the angle doesn't change, so that will be alpha 2. Therefore y2 alpha 2 will be equal to m2 times y1 into alpha 1. This is for the translation. And here M2 is the translation matrix which we already derived in our previous lectures. It is 1 T 0 1. Here T is the translation of the light ray, which is equal to the thickness of the lens. But in our previous lectures, when we were deriving this matrix for the translation, we had written L here, because in that situation the distance covered by the light ray along the optical axis was L, but here it is represented by T. Similarly, for the third matrix, here the refraction occurs at this point, so the coordinates, the final coordinates y3 alpha 3 will be equal to m3 times y2 alpha 2. This is for the second refraction. So telescoping these matrices, these metric equation results, it is easy. Here m3 y2 alpha 2 and y2 alpha 2 is m2 into y1 alpha 1. We should write here, instead of y2 alpha 2, this equation which is m2 times y1 alpha 1, and for y1 alpha 1 we will write this one. So our result will be y3 alpha 3. This will be equal to m3 m2 m1 times y0 alpha 0. Clear? It is easy. Simply it is easy to obtain this equation. Simply put here y2 alpha 2 matrix, which is m2 y1 alpha 1, and for y1 alpha 1 you have to write m1 y naught alpha naught. Clear? So you will get this equation. Evidently, the entire thick lens can be represented by a matrix M. Here, if we multiply these three matrices, which is here M3, let me write M3 also. I have written M1, M2, and let me also write M3. So again, M3 is a refraction. So, but there will be slightly change. Here M3 will be equal to 1 0 NL minus N prime upon N prime R2 into NL upon N prime. Look at here. In the first refraction, the light ray was entering from a medium of refractive index N to a medium of refractive index NL. So here is N minus NL divided by NL, and here the radius of the first interface was R1. And similarly, for this element, the ratio is N divided by NL, the first medium divided by refractive index of the second medium. But for the third matrix, here the light ray is entering from the medium NL to N prime. So I have only changed these elements, which is now NL minus N prime divided by N prime, and here the radii is R2 because the radii of this spherical interface is R2, and into this element is NL upon N prime. Clear? Evidently, the entire thick lens matrix, by multiplying M3 then with M2 then with M1, we will replace those three matrices, which is M3, M2, M1 by M. But remember that multiplication of matrices is associative but not commutative. We should maintain the descending order of the matrices, which is starting from the back. Here the matrix for this one is M3, for the translation is M2, and for this refraction is M1. So we have to write the backward or the descending order for the of the matrices for the multiplication. So we shouldn't write M1, M2, M3. That will change our result. The individual matrices operate on the light ray in the same order in which the corresponding optical actions influence the light ray as it traverses the system. So for any optical system which has n refractions and reflections, similarly translations, for that situation, our generalized matrix equation will be equal to, for n reflections, refractions and translations, whatever occurs in the optical system, the generalized matrix equation will be, this is the final coordinates yf alpha f. This will be equal to m n, because I have written n number of reflections, refraction and translations. So this is the last, for the last refraction or reflection, whatever what happens in the optical system, this is the last matrix, and then it will be n minus 1 and then n minus 2 and so on, and at the last we will get m3 m2 m1 times the initial coordinates, which are y0 alpha 0. This is generalized matrix equation. Clear? And this matrix, ray transfer matrix, is representing the ray transfer matrix, representing these operations, the ray transfer matrix. Representing n operations in the entire optical system. So that will be m is equal to, simply by multiplying these matrices, m is equal to mn times mn minus 1 times so on. This is m3 m2 m1. So this is, let's suppose, equation number 1. This matrix equation, it is for our optical system, which is thick lens. This is used for this one. Clear? And here m3 m2 m1 are written here. So this result which we obtained for our thick lens with index NL and whose thickness is for paraxial rays is T. The correct approximation for a thin lens is then by allowing T equals to 0. So first let me write these matrices first. For a thick lens, for a given thick lens system, which is given in our figure, the ray transfer matrix, it will be m, which is equal to m3 times m2 times m1. Simply substitute these matrices. m3 is 1 0 nl minus n prime upon n prime times r2 into nl upon n prime, then multiply it with m2. This is m3. Now m2 is 1 t 01. This is part of the translation through the lens which is having a thickness t. Clear? And then the first refraction, which is 1 0 n minus nl upon nl r1 into n upon nl. So this is the system ray transfer matrix for a given figure, which is having a thickness T. But when this is our result, this is the result which we are going to obtain, the thick lens matrix. Thick lens matrix. But now we want to change it for a thin lens as well. But as we know that in a thin lens, for a thin lens, T is almost 0, which is having a negligible amount of thickness. And let's suppose we assume that the lens is surrounded by the same medium. It means that to the left and right of the lens, it is having the same medium, and we assume that n is equal to n prime. That means that to the left and back of the lens, it is having the same medium. So this will become this equation. Let me see. This is for with this equation which I have written by equation number 2. This is ray transfer matrix, ray transfer matrix for thick lens. Clear? So you should memorize this matrix. So now we are converting this ray transfer matrix for a thin lens as well, but here we have to make the modification where T tends to 0, which is a thin lens is that one which has a negligible amount of thickness, and we also assume that the refractive index to the front and back side of the medium is of the lens is same. Therefore M will be equal to 1, 0, NL minus N upon NR2. Clear? Into NL upon N. Here we have suppose that N prime is equal to N. So I have just only replace N prime by N here. This is M3. Now for the translation, 1, 0, 0, 1. Here I have replaced T by 0 because for a thin lens the thickness is negligible. So here T tends to 0. And then for the first refraction, that is 1, 0, N minus NL upon NL R1 times into N upon NL. Clear? This is equation number 3. So this is the ray transfer matrix for a thick lens, and this is for a thin lens. Clear? So we should memorize these results. Now if I multiply these matrices first by descending order, we will get, I am not going to multiply each term. I will only write the result which I will obtain by multiplying these matrices. This will be by simplifying. equation number 3. Clear? M will be equal to 1 0 NL minus N upon N times 1 over R2 minus 1 over R1 into 1. So if you can't remember this Rho transfer matrix, so this is the simplified form. This is equation number 4. Here this element of the matrix, Rho transfer matrix for a thin lens, this is by the using of Lensmaker's formula, by Lensmaker formula. This element, which is NL minus N upon N into 1 over R2 minus 1 over R1. This is 1 upon F. Clear? So I can write it here. But if you see here, this is R1, sorry, this is R1 and this is R2. Clear? So if I take negative sign from here, so it will become like this one. Therefore, so for a thin lens, the Rho transfer matrix would become M is equal to 1 0 minus 1 upon F into 1. This is a Rho transfer matrix for thin lens. This is equation number 5. Here, as usual, F is taken positive for a convex lens and negative for a concave lens. Here, if the thin lens is convex, so it will be positive, while if the thin lens is concave, that will be negative. This matrix and those previously derived, which we already derived for the translation, for the reflection, and for the reflection from a spherical interface, almost I have written here all those. So this one is for the refraction from a spherical interface. This is for the translation through a homogeneous medium, and again this is for the refraction through a spherical interface. And this one, it is the Rho transfer matrix for a thick lens, and this one, which is in the simplified form, it is for a thin lens. So thank you very much.